Okay, so we're going to pick up where we left off last time. We were just doing looking at the relationship between delta G, which reflects spontaneity of a reaction, and the value of E. The only real purpose of this equation here is to make that comparison between these two. It's really not intended to do any other calculations if you happen to be given a bunch of random information. It's just the idea to compare these two values and give an idea of the spontaneity in regards to electromotive force, or in delta G spontaneity, Gibbs free energy. Let's define what some of these terms are, which we probably mostly already know. N is the moles of electrons transferred. I think there's two R's here. I could be wrong on that. Figure it out. N is the number of moles of electrons that are transferred in this reaction. And F, and again, F is many times written in some like cursive-y thing, but my cursive is terrible, so I won't be using it. And F is Faraday's constant. And this is in your packet that you would have in any test. That relates coulombs, which is electrons, charge of electrons, coulombs per mole, or to joules, volts per mole. They're kind of within their interchangeable with these two things here. And again, as far as what it is equal to a Faraday, and to put this more specific in here as far as a number for a Faraday, 96,485 coulombs per mole. So again, a mole would being Avogadro's number, and we had the value for electrons. Top of my head, I can't remember what it is, 1.6 times 10 negative 19 or something like that. If you put those two numbers together, out will jump Faraday's constant, 96,485. Okay. And delta G, just by comparison and looking at this equation up here, delta G is directly related to E. They're on opposite sides of the equal sign, so if one goes up, the other goes up. And this negative sign will kind of relate that to it. All right, three equations that we kind of want to just make a comparison of. Actually, let me hold off on that. I'll get there in just a moment. I want to introduce them first. Relating K to E. So we're bringing in another value, equilibrium. Yeah, we can do that. Under standard conditions, delta G is equal to delta G prime, which is standard, plus RT natural log Q. No, actually, let me back up here. I said under standard conditions. So delta G is equal to negative RT natural log K. So under standard conditions, you are at equilibrium, and therefore that is reflected in delta G. Okay, if I'm not at standard conditions, I have that delta G value, but based upon this equilibrium, which is no longer at equilibrium, I'm at a Q value, that is going to be related in comparison to this and throw it somewhere off value, and that is going to give you the conditions that you're at, delta G. Okay. Now to make the comparison to what we were doing up here is I have this value from the previous chapter, 19, and I have the equation just above, delta G is equal to negative N Fe. So we have that equation. We can relate both of these over to another equation. E is equal to RT and F natural log K. Just doing some substitutions for delta G into this equation here and moving things around. So now we have three different comparison equations that we could use depending upon the information that was given to us. If I had delta G and I wanted to relate over to E, I could do that. If I had delta G and I want to relate it over to K, I can do that. And if I wanted to relate E over to K, I could do that as well. So all three of these equations can be manipulated around to find the other variable between E, K, and delta G, depending upon which information was given to you. Okay, given this equation here, we can make another comparison based upon the relationship that we have with delta G and negative ENF. We can make a substitution into that, and you don't necessarily have to memorize this, but I'm just going to derive it really quick. Standard conditions plus RT natural log Q, and then given this as far as common values in comparison, we would have E non-standard conditions compared to standard conditions plus the negative RTNF natural log Q. And then if we roll some numbers around as far as values that are constants within here, and change it over from natural log over to log, which is this whole 2.303 log value, and I guess of Q, which we're doing the comparison of, we can rearrange this and give us a new value, or a new equation, excuse me, 0.592. This grabs a hold of the R value as well, log of Q. This is what is called the Nernst equation. I'll put that right down here, N-E-R-N-S-T equation. What this allows us to do is, given some non-equilibrium values, right? You're given the equation of concentration of this, this, and this, or pressures of this, this, and this, we can place this into this equation here, get the log of that, and then based upon the number of electrons that are exchanging from right side to left side, or left side to right side, excuse me, and compare that to what is the standard value for that equation, what is the potential electromotive force of the system. So again, given some non-standard concentration conditions, we can get a value for the electromotive force for the system. That is the purpose of that equation. Okay, so let's get a kind of like, what am I supposed to do with this? Let's focus on Q, which again, from based on 3 previous chapters, 15, 16, and 17, products over reactants. Don't forget the whole exponential thing with that, raised to whatever powers. So comparatively, as Q becomes larger, E decreases until E is equal to 0. So again, think about it. As Q increases, meaning products, I start loading in more and more products. For any equation, if you start loading in the products based on the Chatelier's principle, it's going to be more and more difficult to push the reaction in the forward direction towards products. So therefore, the E, which a more positive value, means the reaction is spontaneous in the forward direction, it keeps going down and down and down until it gets to a value of 0. And we'll just mention that here. At E is equal to 0, there is no potential. The reaction does not move forward. Okay, that's a good place to take a break, and we will start a new problem in the next lecture.